All right, before I go to the notes here, let me show you something. Suppose you have a parabola, right? I don't know, suppose this is x equals 5. And suppose you find the point right there, 5 comma whatever, and then you draw the tangent line, right? Yeah, so there's a tangent line. Now, all right, what do you notice nearby, like at 4.9 or 5.1? So nearby, what do you notice? That the y value on the green parabola is very close to the y value on the red line. Everybody agree? Yes? Everybody agree? That those y values are really, really close? So at 4.9, if you look at the y value on the green parabola versus the y value on the red line, aren't those y values really close? Now obviously the further away you go from this point, where you have the tangent line, you know, the further away the y values will be. Do you agree with that? So this is what today's lesson is all about. It's called local linearization for obvious reasons, or linear approximation. And so what we're going to be doing today is we're going to be using the tangent line equation, right, as an approximation for the y values on the parabola. And you might wonder, well, why would we want to do that? Well, think about it. In order to, you know, if you don't have, for example, if you don't have the function here, okay, then it, you know, it'll be difficult to use the function itself, okay. And then the other thing is, you know, it's real quick and easy to, if you have the tangent line, to find the y values on a line, right? Makes sense? So again, and I'll talk more about the reasons why as I show you more examples, but just know that this is an option. If you just want a quick estimate of the y values there near the point 5 comma whatever, you can simply use the equation of the tangent line to approximate the y values or function values on the parabola. Okay, so that's what we're doing today. Okay. So, and again, it doesn't really matter what the function is. It doesn't have to be a parabola. Okay, so everything I just talked about is here. The only thing is, to write the equation of the tangent line, I recommend you use the point slope formula instead of y equals mx plus b. But then after that, you can change it to y equals mx plus b, right? If you want to, right? Okay. So, everybody do example 1a and b. Okay, everybody do example 1a and b for me. Okay, so in part A, we're just graphing that parabola by plotting some points. So if you put a 0 in, what do you get, guys, for the y value? 4. How about a 1? 3. And when will the y be 0 when x is what? 2 and negative 2, right? All right, so that gives us a bunch of points to plot. And by the way, you kind of already know that it's a parabola shifted up 4 units and opening downward, right? As well. Shani, you with me? Yeah. Okay, so with all that in mind, I know the parabola goes through that point, that point, that point, this point, and by symmetry, won't there be another point over here? All right, so just connect those to draw the parabola. All right. And then at that point, I wanted to write an equation for the tangent line at the point 1 comma whatever. So what is it? 1 comma what? 3. So at the point 1, 3, we can draw the, we can write the equation for the tangent line by first finding the derivative. And so what's the derivative, guys? What's the derivative function? Negative 2x. So at the point 1, 3, if you plug in the 1, you get what for the slope? Negative 2. All right, so now that you got the slope and the point, you can use the point slope formula to write the equation of the line. And then what, add 3? Okay, so everybody agree that that's the equation of the tangent line, which we can now graph. You can either plot points or use M and B, I don't care. I'm just going to use M and B. So I know it goes through 0, 5, that's the y-intercept. And then you go down 2, right 1, down 2, right 1. Okay, and so if you connect those points, you're going to get the tangent line. Okay. All right, so basically then, as you can see, remember this is the point 1 comma 3, isn't it right here? Isn't that the point 1 comma 3? Thank you. So near that point, aren't the y values on the line close to the y values on the parabola, aren't they? Near that point, obviously the further away you get, the worse the approximation would get, but they're pretty close, near the point 1, 3. So what I did here for you is I just wrote the actual function, and then this is basically, you can use that as the approximation for the y values, right? So I'm going to call that f of x approximation. Okay, so you can use the tangent line to approximate the y values. And then if you want, you can compare them to the actual y values. Got it? All right. So using the tangent line, I get what? What's negative 2 times 0.8, guys, plus 5? What is it? You can do that in your head. What is it? 3.4? Yes? Got it? And then you can just keep doing this. What is this? 3.2? Right? And so on. All right, so does everybody understand what we're doing here? That those are the approximate y values using the tangent line, right? Now, obviously, it's not going to be exactly the same as if you actually plug the 0.8 and the 0.9 and the 1.1 into the function itself, but these are pretty good approximations for those y values. Got it? Okay. Now, everybody read D, and I'm going to have Colin somebody to fill in the blank for me. So everybody read D and think about what word goes in the blank, or words. All right. How about, what am I going to call on here? All right, Jonathan, what do you think? What goes in the blank? Well, look at it. At the point 1,3, is the parabola concave up or down? Concave down. And so doesn't that make the tangent line lie above the curve because of the concavity? And so what do you think? Are those linear approximation values greater than or less than the actual parabola y values? Okay. Everybody agree they're greater than the actual y values? So do you agree that the concavity determines this? Okay, and so if you had to answer that same question without looking at the graph, what would you do on paper to figure out the answer to that question? If you didn't graph, you didn't have time to graph, or it was too complicated to graph, how could you answer that question without graphing? What would you do? Yes? Okay, yeah, you're right. But what's the way you could prove it, though, using calculus? I'll give you another chance. Well, what did we just say? What determines this, the concavity? And how do you figure out the concavity at a point? Find the what? Second derivative, right? And then plug in a 1. So if f double prime of 1 is positive, that tells you f is concave what? Up, which means the tangent line would be below the curve, right? Which means the linear approximation values would be less than the actual y values. If f double prime of 1 was what? Negative, that means what? At that point, f is concave down, which means the tangent line lies above the curve, and therefore the approximation would be greater than the actual y value. See how I figured all that out without actually knowing the graph? Yes?
Why do you need to use the approximation if you have the actual formula?
Again, sometimes it'll be just a little bit easier to get quick approximations, right? I mean, you know, here we just had to quickly plug in an x value and we got the y values in like 2 seconds. So if you just need an approximation without actually needing the exact value, this will give you an idea what it is. And again, you'll see other examples where it might be easier to do it this way versus the regular way. Okay. All right, so let's go to the next example. All right, somebody tell me what to do here. We'll do this together, but you got to tell me what to do. So, all right, Serena asks, what should I do here? How should I start this problem? There's my equation. Yeah, well, not integrate, you mean? Yeah, differentiate that, and because of the way it's written, I have to use what? What type of differentiation? Don't I have to use implicit differentiation to get the derivative of that thing? Yes? Okay. And then go from there? Okay. Okay, so here we go. Remember, anytime you differentiate something with a y, you got to put a what? dy dx. Now, so everybody agree the derivative of that is 2x? Now here, this is what I'm going to do. I'm going to pull out the minus 3, so to speak, and then I'm going to use the product rule on xy squared, right? So using the product rule on xy squared, I get derivative of the first times the second plus the first, and then times the derivative of the second. And don't forget to put your dy dx there. Okay. Okay. Let's see. Okay. All right, so then continuing, don't I get plus 3y squared, then I got to put another dy dx, and then equals the derivative of 11, which is 0. All right, so once you've gone through that first step where you differentiate everything and put it, multiply by dy dx anytime you differentiate a y, your next step is to get the dy dx terms on one side and move everything else to the other. Is this ringing a bell? Okay, so here we go. Let me simplify this first. I'm going to distribute that minus 3. Okay, and then from there I'm going to move this and this to the right side. And then I'm going to pull out the dy dx. And then I'm going to divide both sides by that. All right, and so you want to get the slope now at the point 5,1, so you can write the equation of the tangent line. Okay, so what should I do now? Replace all x's with what, Gloria? The 5. And then replace all the y's with what, Alex? 1, okay. All right, so if I simplify this mess, what do I get? We agree you get 7/27 here? Okay. And so now I'm going to write the equation of the tangent line by doing y minus 1 equals that slope times x minus 5. Simplify. Okay, so everybody agree that's the equation of the tangent line there? At the point 5,1, right? And what we want to do now is we can say that that's an approximation for the function for the y values on the original graph, whatever that looks like. So I'm going to use the tangent line, and then I want to approximate what values? F of what? Yeah. So f of 1.8 would be, and again, you have to use your calculators here. Yeah. Oh, 4.8, thank you. Not 1.8, sorry about that. All right, thank you. You get approximately 0.948, right? And then you can do it again to get the approximate value of f of 5.1. Okay, you guys are pretty quiet. Is this making sense or not? Yes? Okay? All right. All right, so we're good on that. Next page. All right. example 3 is much easier than it looks. You shouldn't have to do a whole lot of calculus, but go ahead and see if you can do example 3 in your groups, okay? Should only take you about 2 or 3 minutes in your group. So go ahead, everybody, work on example 3. Again, there shouldn't be a whole lot of work. I gave you everything you need if you read the problem carefully. All right, Sid, what'd you guys write? Y minus 5 equals x minus negative 3, which turns into x plus 3, right? And then you just change the slope-intercept form, right? All right, so there's a tangent line, which can now be used to approximate the y values or function values at points near negative 3 comma 5, right? And isn't negative 2.9 near the point where x is negative 3? And so that would be, this could serve as a pretty good approximation. Yes? So just plug the negative 2.9 in here. What do you get? 5.2? Is that right? Yes? So again, with this information, we were able to actually approximate the y value nearby without actually even knowing what the function is, right? You understand that we didn't even know what the function was, and we were still able to get an approximation for the y value without even knowing the function. Pretty cool, huh? Got it? Okay, so there's another advantage to using this concept. Okay. Okay, this is a AP question from a few years ago, 2010, I believe, yeah. So I want to see if you guys can do it. So everybody read it and see what you can get. Okay, start writing something down, guys. again, if you read this problem carefully, they don't tell you what the waste function W is, do they? They only tell you what the rate of change of that is. In other words, they only give you the derivative function. But that's okay. If you use linear approximation, which is what it expects you to do, you don't even need to know what the original function is, do you? Do you? No. All right, so think about that. I mean, yeah, you might be able to separate variables and find the original function, but is that even necessary on this question? No. Now, if you use linear approximation, you don't have to go through all that work. You can just approximate what you want using the concept you learned today. All right, here we go. All right. So James, what did you guys do? Okay, so the variables are t and w, where t is the control variable and w is the kind of like the y value, right? And so you said you wrote the point 0, 1400. Everybody understand why you wrote that? Because of that. The beginning is time equals 0, isn't it? So he wrote that as the point, right, where we want to write the equation of the tangent line at, right? And then what did you do to find the slope? Okay. And so doing that, and that gave you, 1100 over 25, which equaled what? 44? Is that what you said? Okay. All right, so that's the slope. And so then I'll go to somebody else. So Max, so what did you do to write the equation of the tangent line at this point? You write y minus what?
Y minus 1400
Okay.
equals 44 x minus 0.
Okay. And by the way, to make it more meaningful, instead of using y and x, is it okay if I switch to w and t? Is that okay to make it more meaningful here? So I'm going to have w minus 1400 equals 44 times t minus 0. And I'm just going to do the algebra now to get it in y equals form. So is that what you guys got for the approximate w value equation? Yes? And so now we want to plug in what? Yeah. Okay, because remember, if t is in years, then 3 months is how many years? If t is in years, as it said it was, then 3 months would be how many years? 1/4 of a year. You understand why you're supposed to use time equals 1/4 instead of time equals 3? Is that clear? Okay, so doing that, so after 3 months, you can approximate how much waste is going to be in there by plugging a 1/4 in for t. And what does that give you, guys? 1411? What's the label? Put units on your answer. Tons of waste. Just like you're going to waste tons of your cooperation points if you don't work after a short break. Right? Got it? Okay, so that's it. I gave you the concept. I showed you a couple different AP scenarios where you might have to use this. Okay, so if they throw one of these on this year's tests, at some point you'll have a good idea what you need to do, right? Okay, now, the good news is you have no book work. I gave you, let's see, 1, 2, 3. I gave you 5 problems on a worksheet on what you learned today. And then after that, I gave you a bunch of review problems for the rest of the test. If you can do this whole packet. Test should be pretty easy. Let me see something. I gave you a good variety of stuff. I gave you some slope fields. I gave you a bunch of solving differential equations, separating variables. So I'm telling you, if you can do this whole packet, including this, new stuff I gave you today, test shouldn't be too bad. And again, the test is Friday. Okay? All right, so you can take a break for about 4 minutes to 8 o'clock, then you'll have like 45 minutes to work on this stuff. And by the way, did I give you answers to all this? I think I did. Didn't I, at the very end? Yeah, I gave you the answers to the 5 homework problems for today's stuff, and then I gave you all the answers to the review. So you shouldn't really need anything else to prepare for the test. Got it?